looking at this one, butane gas is combusted according to this equation when 4.14 grams of butane reacts with excess oxygen gas. And so in this case, butane's the limiting reagent, oxygen is the excess. We don't need to know how much oxygen, just as long as it's excess. So we're going to calculate the theoretical yield based on this. And so this must be the actual yield here. So this is another example of calculating the percent yield. It's not the one I wanted. The one I wanted is this one, calcium cyanamide. Okay, so how much ammonia? Let's go with 7.25 grams of calcium cyanamide. So 7.25 grams of calcium cyanamide, CaCN2. We're going to go from grams to moles. So calcium is what? 40.08. Carbon's 1201. 2 nitrogens. 1401 times 2 is 2802. So 80.11 grams of CaCN2 per mole of CaCN2. Okay, so the grams cancel, and then where? You go from here. The moles of ammonia. So let's move around. We got 2 moles of ammonia for every 1 mole of CaCN2. Okay, then where? Yeah, grams of ammonia. So nitrogen is 1401, and then we have 3 hydrogens. Each one is 101, so 303, so this is going to give us 1704. So 1704 grams of ammonia. Mole. If we stop here, this is called the theoretical yield of ammonia. So theoretical yield of ammonia, because we have excess water. So we got plenty of water to react, or at least stoichiometric amount of water. So calcium cyanide is the theoretical yield. So if we stop here, what is our theoretical yield? 7.25 divided by 80.11 times 2 times 17.04. 3.08. And so the theoretical yield is going to be 3.084 grams of ammonia. That would be the theoretical yield. But we have to account for losses. You know, that's the amount we'll get in theory, but how much are we going to lose? We're going to lose a certain percentage of that. And so if that's our theoretical yield, then we're not going to get that in actuality, because the actual yield is going to be 92.8 grams actual yield for every 100 grams theoretical yield. And so for every 100 grams, I'm only going to get 92.8. That means I'm going to lose 7.2 grams out of 100. I only have 3.08, so that's going to be times 92.8 divided by 100. 2.862. And so in actuality, I only expect 2.862 grams of ammonia. And so I'm going to lose a little bit of the ammonia due to losses. So we call this the actual yield here. And so for every 92.8 grams actual yield of ammonia, I'm going to have have to have 100 grams of theoretical yield ammonium. So that's calculation of the actual yield. Let's go on to number 35. In number 35, what we're doing is we're going to compensate, the amount of ingredients here. Because we want this as an actual yield. We want 500 kilograms of ammonium actual yield. If we want a 500 kilogram actual yield, how much hydrogen do we need to start off with? Let's take a look. So 5.00 times 10 squared kilograms of ammonia actual yield. So in theory, how much should I make? If I want 500 kilograms net, then I'm going to have to produce more because I'm going to lose some. So how much? Well, I have an 88.8% yield. There's an 88.8% yield, and what that means is I'm going to have to produce 100 kilograms of theoretical yield ammonia for every 88.8 kilograms of actual yield of the ammonia. And so if I want 500 kilograms, I have to plan on making a lot more because I'm going to lose 11.2%. And so how much? So 500 times 100 divided by 88.8. Which means if I want 500 kilograms of actual yield, I better make 563 kilograms of theoretical yield. Because I'm going to have to plan on losing 63 kilograms. And okay, so if I need to make 563 kilograms worth of ammonia, well, how much hydrogen do I need? So I'm going to go from kilograms of ammonia to grams of ammonia, 1,000 grams per kilogram. So I got grams of ammonia, from grams of ammonia to moles of ammonia. 1704 grams of ammonia per mole of ammonia. And then from moles of ammonia to moles of hydrogen, it's 3 moles of hydrogen for every 2 moles of ammonia. And then the molar mass of hydrogen. Molar mass of hydrogen is 1.008. I'm going to go to 4 sig figs there. So that's going to give me 2.016 grams per mole. Since I'm working with kilograms, I'm going to convert this to kilograms. So a kilogram is equivalent to 1,000 grams. And so this should give me how many kilograms of hydrogen I need to make 563 kilograms of ammonia, in which I'm going to lose 11.2% of that. And so this is 500 times 100 divided by 88.8. Times 1,000 divided by 1,000 to cancel, so we'll do divided by 17.04 times 3 divided by 2 times 2.016. So I need to make 99.92 H2 kilograms. I need 99.92 kilograms of hydrogen. I need 99.2 kilograms of hydrogen to make 563 kilograms of ammonia, of which we're going to lose 63 kilograms and be left with 500 kilograms. Does that make sense? Uh-huh.
So we would do the molar ratio of hydrogen as a molecule instead of as an atom?
Yeah, we would do it as a molecule because the hydrogen I'm talking about is H2 from this equation here. And so this is what you're going to buy. So if I'm going to buy hydrogen, I'm going to buy 100 kilograms worth of hydrogen.
Okay. So it's not like in every situation we would use it.
No. In a lot of situations, if I'm looking at the percent by mass hydrogen in ammonia, then it would be per atom of hydrogen. But since this is H2 in the equation, I'm going to use H2 here. Because when you go to the store to buy the ingredients, they aren't going to call it H, they're going to call it H2. Let's say if I didn't have this loss. If I didn't have this loss, then I don't have to buy as much hydrogen. If I didn't have this loss, how much hydrogen would I have to buy? And so let's say I had 100% yield. I didn't lose any. And so it's 100 out of 100. And so let's redo that calculation. Oh, I shouldn't have deleted it. We'll redo it. And so 500 kilograms, 100 out of 100 is 1,000 divided by 1,000. The same, so this is going to be divided by 1704 times 3 divided by 2 times 2.016. If there is no loss, if 100% yield, that is, there's no loss, I only need 88.73 kilograms of hydrogen. But since I only have 88.8% yield, then I have to buy more hydrogen. I'm going to have to buy an extra over 10 kilograms worth of hydrogen extra because of the loss. Hydrogen's expensive. The nitrogen's cheap because where does the nitrogen come from? The air. So it's cheap. So nitrogen is going to be in excess, hydrogen is going to be limited. Okay, are there any questions with this? Okay, so let's take a look at number 36 here. Hydrogen iodide is a colorless, non-flammable, and corrosive gas with a penetrating, suffocating odor. It forms hydroiodic acid in water. It can be prepared by direct reaction of its elements, hydrogen plus iodine yields HI. It is desired to produce 331 grams of hydrogen iodide in a process in which the percentage yield is 71.1%. How many grams of hydrogen gas will be needed? And so in this case, we're going to have to make more. This is the desired, this would be the actual yield. And so in theory, we're going to have to make a lot more because we're going to lose a lot of it. In this case, we're going to lose 28.9% of it. And so the theoretical, in theory, we've got to make a lot more than this. If we've got to make a lot more, then we've got to calculate how much hydrogen gas is required to make that. So this problem is just like the previous problem. If we look at number 37 here, calculate the percentage yield. Well, this one is like the earlier problem. Here, they give us 7.03 grams of carbon dioxide. Water's cheap, so it's cheap and plentiful, so it's got to be in excess. This is limiting. We can calculate that. Yeah, in fact, did we do that one? So we calculate the theoretical yield based on limiting reactant being CO2 here, 4.80. We don't have to do the other calculation because we're assuming it's excess H2O, step one. And then the actual yield is 392. Theoretical yield is 480. So it's about 80% yield. Okay, the last part of this book deals with energy. So let's take a look at it. The energy units that we use, the calorie. Calorie is abbreviated CAL. There are actually two calories. There's the one with the lowercase c, and there's one with the uppercase C. The one with the uppercase C, the capital C, is the food calorie. And the one with the small c is the chemical calorie. The only difference is that a food calorie is 1,000 chemical calories. In other words, a food calorie is equal to 1 kilocalorie. Chemistry calorie. This is to make the numbers more, because the calorie is kind of small. And so a typical diet provides about 2,000 calories. These are food calories. But in terms of chemical calories, the typical diet would be 2 million chemical calories per day. But if you're eating 2 million calories, it's the hassle. Like to keep the numbers small. The calorie as defined is this. It's the energy required to raise the temperature of 1 gram of water by 1 degree C. So if you take a milliliter of water, how much energy does it cost to increase the temperature by a degree C? Well, it costs 1 calorie. That's how it's defined. Another common unit is the joule. In fact, the joule is more common. The joule has a physics definition. And the definition goes like this. If you take a kilogram weight and raise it by a meter against gravity, the amount of energy that it takes to take a kilogram and raise it by a meter is 1 joule. It turns out that in 1 calorie there are 4.184 joules. That's how we can convert from one to the other. And so the first types of problems we do are energy conversion problems. Your book likes these types of conversions, like this. I just like to remember one, kcal to kJ. Your book likes to use kilomoles or kilo molecular mass or molar mass or whatever. And so the ones you need to remember are 1 food calorie is equal to 1,000 chemical calories. And 1 chemical calorie is equal to 4.184 joules. Joules has a physics type definition where you lift a mass, the calorie is just heating water. And so we'll do some conversions here. A 1 ounce serving of almonds has 1.6 times 10 squared calories. So 1.6 times 10 squared calories is 160 calories. Express this in joules and kilojoules. So if we have 160 calories like this, then I know that there's 1,000 little cows per 1 big cow. And so that'd be 160,000 calories, little calories. And then I know that there's 4.184 joules per little cow. So what does that come out to? So do 160 times 1,000 times 4.184. 669,440. 669,440 joules. Those are big numbers. And so rather than expressing this in joules, we'll express this in kilojoules. So this would be 669.4 kilojoules. Something like that. Actually, I'm not even allowed that many sig figs, am I? And so to round this to the correct number of sig figs, this would be 6.7 times 10 to the 5th joules. this would be 6.7 times 10 squared kilojoules of energy. So let's check that. 6.7 times 10 squared kilojoules, which is 6.7 times 10 to the fifth joules. They use this other conversion factor, which I don't bother with. So those are inner conversions. Typically, when we're looking at chemical reactions, we look at the energies associated with those. The energies that are associated with endothermic and exothermic reactions is called the heat of reaction. Heat of reaction. More formally, it is the enthalpy of reaction, delta H. This delta sub RH, this is called the heat of reaction, or enthalpy of reaction. Enthalpy. We'll talk about enthalpy later. And so we have exothermic and endothermic. And so when we take a look at those, exothermic processes are going to increase the temperature. Endothermic processes will decrease the temperature. Decrease. This is an exothermic process here. Increases the temperature. Start off at 23, end up at 29. That amount of energy is fixed. So here's combustion of ethane. When we combust 2 moles of ethane, we see that the heat of reaction, or the enthalpy of reaction, is minus 2855 kilojoules. And so what that means is this. It means that we lose 2855 kilojoules. And so this negative sign here just indicates the direction. So let's say your bank account, you see minus $20. Minus $20 to your bank balance. Does that mean you deposited a minus $20 bill into your bank? No, it just means that the balance dropped by $20. And so, like money, there's no such thing as negative energy. And so, although this looks like negative kilojoules, it's not. This just means that this went from here to here. In the process of going from here to here, it must have lost 2,855 kilojoules worth of energy. And so what we could do is we could show that in an equation like this. When we burn 2 moles of methane and 7 moles of oxygen, we're going to produce 2,855 kilojoules. That is, we're going to give off that much energy. So things are going to get hot when that happens. So this is exothermic. So 2 ways of expressing it's exothermic. 1, we could have a negative showing that it's losing that energy. Or 2, we can write it as a product. When we have an endothermic reaction, it's just the opposite here. Here, this means we're gaining. So we're starting off lower energy and gaining and go higher in energy. 92 kilojoules plus. And so when we do this, 2 moles of ammonia breaks down into nitrogen and 3 hydrogens. It's going to cost us 92 kilojoules. Or we can show that cost here. 92 kilojoules will be a reactant, and it's going to be consumed. So energy is consumed. When it costs us energy like this, things tend to cool down, don't warm up. Now, it depends on how much reaction we have. So this is 2 moles. What if we burned 1 mole of methane? If we burn 1 mole of methane, are we going to get the same amount of heat? No, we're going to get, well, if we burn 1 mole, we're going to get half as much heat. What if we burn 4 moles of ethane? This is ethane, not methane. Sorry. If we burn 4 moles of ethane, you know what's going to happen here? You get twice as much heat, burning 2. And so heat is what we call an extensive property. It depends on the amount. So the more fuel, the more heat you're going to get. It also depends on the state. So which one's more stable? Gaseous water or liquid water? Which one's, liquid water is more stable. So we're going up here and we're dropping down. If we're up here and we drop down 2,855 kilojoules, then we're at this state, CO2 and water. But the water is gaseous. If we want liquid water is more stable, so it's going to be a bigger drop. And so if this were liquid water, we'd be up here and drop all the way down. Liquid water being more stable than gaseous water, it's going to release a different amount of heat. And in fact, it does. If we just simply change it to liquid water, we're going to release 3,119 kilojoules rather than 2,000. It makes sense to use liquid water here because most reactions take place at room temperature. Room temperature being 25 degrees C, 77 degrees. So what we can do is we can do stoichiometry with this. When we do stoichiometry, we look at the stoichiometric ratios, 2, 7, 4, 6, 28, 55. And so we can do the stoichiometry based on mole ratios. Let's say we burn 14 moles of oxygen. If we burn, or that is, we consume 14 moles of oxygen, then we know it's 2855 kilojoules per 7 moles. We have 14, it's double. So we're going to have twice as much. And so let's take a look at some thermochemical stoichiometry problems here. Start out with 57. Energy is transferred from sunlight in the photosynthesis reaction in which carbon dioxide and water vapor combine to produce sugar and release oxygen. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar formed. What are we supposed to do? We're supposed to write the equation in two ways. So first, let's go ahead and write the equation for photosynthesis. And so photosynthesis takes CO2 and water, CO2 gas, and H2O liquid to produce sugar, C6H12O6, sugar solid, and oxygen. Is energy consumed in photosynthesis or is energy produced in photosynthesis? It's consumed. The energy is going to come from the sun. So energy is going to be reactant here, 2.82 times 10 to the third kilojoules, 2.82 times 10 to the third kilojoules plus. Okay, now we got to balance this. So let's balance this. We'll need 6 CO2s. We need 6 waters, and we're going to form 6 O2s here. Now, usually, this is per mole of sugar formed, so we got to make sure we have 1 mole here of sugar. So if we form 2 moles, then it would be double this amount of energy. 3 moles would be triple this amount of energy. So this would be one way of expressing this. This would be energy as a reactant. The other way of expressing this would be 6 CO2 gas plus 6 H2O liquid yields C6H12O6 solid plus 6O2 gas. And then we have delta R sub H. The heat of reaction is equal to plus 2.82 times 10 to the third kilojoules. So those would be the 2 ways. for an exothermic reaction would be the opposite, 61. The reaction of oxyacetylene torch is highly exothermic, releasing 1.31 times 10 to the third kilojoules. Note they didn't say releasing negative 1.31. You know, because there's no such thing as negative energy. So you aren't going to release negative energy. It's like releasing. I'm going to release negative $20 bills. If you release negative $20 bills, you know, is there such thing as a negative $20? No, but maybe you meant that you're losing or you're giving away $20 bills. That's what the negative means. So that would be correct. And so for every mole of acetylene, and so it depends on how many. So we just are concerned. This has to be 1 mole of acetylene. So when we look at the equation, it's going to look like this here. This is a case where we have to use fractions here, because this is per mole of acetylene. In order to get rid of this fraction, we have to double the equation. Well, if we double the equation, we're going to have to double the heat as well. And so we'll just leave it in fractional form. That way we get it per mole of ethane. So 1.31 times 10 to the third kilojoules per 1 mole of ethane. This would be in its standard form. Most of the time you're going to see it in the second form, not in the first form. But either one's okay. Okay, the second form helps us for stoichiometry. All these. So let's take a look at the stoichiometry problem. Quicklime, the common name for calcium oxide, is made by heating limestone, calcium carbonate, in slowly rotating kilns, which are a type of oven. The reaction is this. This is a pretty interesting reaction. There's some documentary on Netflix regarding this one. The Romans did this reaction. The Romans had access to coal. You need very high temperatures for this. So they took the calcium carbonate. They had coal that they could burn to get to high temperatures to form calcium oxide. CO2. Then they used the calcium oxide to make concrete, and then they came up with all those structures, concrete structures, aqueducts, Colosseum, etc. So this is critical. But what quantity of energy in kilojoules is required to decompose 5.80 kilograms of limestone? So this just turns into a stoichiometry problem. 5.80 kilograms of limestone, which is calcium carbonate. And then we're going to go from kilograms to grams, 1,000 grams per kilogram. And then grams to moles. And so calcium is 40.08, carbon is 1201, 3 oxygens will be 48.00. It's 90. 100.09. And so each mole of calcium carbonate weighs 100.09 grams. So grams cancel, kilograms cancel. Gives us the moles of calcium carbonate. Now we can use the mole ratio here. There's going to be 178 kilojoules for every mole of calcium carbonate. Now we don't use a negative sign because what we do instead is we say consume or produce. In this case, the heat is consumed. So we'll just add that there. If this were negative, then we'd say produced as a product. So let's go ahead and calculate this. This is going to be 5.8 times 1,000 divided by 100.09 times 178. $10,314 kilojoules. And And how many sig figs? We're allowed 3 sig figs, so we'll just go 1.03 times 10 to the 5th kilojoules. That's the quantity of energy required. So let's see what they got here. Come on. Oh, let's see what I did. Not 10 to the 5th, 10 to the 4th. 1, 2, 3, 4. Okay, so that's an example of a thermochemical stoichiometry problem. Let's do one more quickly here. The quick line produced in question 63 is frequently converted to calcium hydroxide, sometimes called slate lime, by an exothermic reaction with water. So if we take quicklime and react it with water, we will form slate lime. This is an example of a Lewis acid-base reaction. What mass in grams of quicklime was processed in a reaction that transferred 291 kilojoules of energy? So let me just finish off this problem here. So normally the way this is written is, this is calcium oxide solid plus H2O liquid. This yields calcium hydroxide, a Lewis acid-base reaction, solid. Delta RH, the heat of reaction for this is minus 65.3 kilojoules. This is the way it's normally written, minus 65.3 kilojoules. And so what mass in grams of quicklime was processed for 291 kilojoules? 291 kilojoules of energy. So there are two ways you could do this. Way one is, this is kilojoules of energy released. And so the two ways you can do this is you could go minus 291 kilojoules because that's energy that's released, and then you could use this conversion factor here, that is 1 mole of calcium oxide solid for every minus 65.3 kilojoules, whereas the negative sign is telling you it's released. Or what you could do is you could just say, well, a positive 291 kilojoules released, and then 1 mole of calcium oxide solid for every positive 65.3 kilojoules released. So rather than putting the negative sign, we just put the word here. It was lost, it was released. And so those are the two ways you could do it. Which way is typically done? Which way is typically done is this second way here. You know, although the first way is done as well, depends on what we do with the sign. So it doesn't really matter. For stoichiometry, it's typically done this way. For other thermochemical calculations, we might actually do it this way here, so that we can keep track of the sign convention. But whatever it is, you have to be familiar with both ways of doing it. But since we're out of time, we'll finish this next time. See you tomorrow.
Maybe you get one day after 6.